So the closest we've got to a theory on everything. Okay, that's a big deal. If that's even possible. I always thought that would never even be possible because a theory on everything would be a lot of theories, right? And a lot of things to explain, right? But let's check this out. This might be a some revolutionary right here.
This is a video about a single simple rule that underpins all of physics. Every principle from classical mechanics to electromagnetism, from
Bro,
quantum.
what was that? Was he just stepping on a board that was floating? You gotta be kidding me. And what type of sci-fi show was that? That didn't even look like a sci-fi show to me. That looked like it was real life, like he was actually on top of a board that was floating mid-air. Hold up here. Do they actually have that in real life? I'm not talking about one of them boards you skate on that got them wheels underneath it. I'm talking about them boards that ain't got nothing. It's just like silver and it floats mid-air. Alright? Nah, that would be crazy. It really looked like that's what he just got on there for a second, y'all. So let's get back to the video real quick. But if they have that, I definitely want one, you know.
Quantum theory to general relativity, right down to the ultimate constituents of matter, the fundamental particles. All of it can be replaced by this single rule.
What?
Feels like we're approaching spooky territory.
What was that? All I seen was an 85.
I hear you, and
Oh, I'm sorry, y'all. All I seen was an 85 and a 0. So this is gonna be interesting. Let's check it out.
I agree.
It may in fact explain the behavior of life itself.
I think I'm stuck in some classical mindset where, to me, the local picture,
Y'all seen that dog? How the dog was running through the water like that? Dogs love to run through puddles of water for some reason, bro. They just love getting their little paws in that water and just going with it. They love it. You know, if you ever have like if you ever let your dog out while it's raining and stuff, boy, they go crazy. You know, but some of them like it. I had a dog already who didn't even like to go outside when it was raining. He would look outside that door and see that it was raining when I'd be letting him out, and then he'd come right back in without even going out.
differential equation way of thinking about the universe, that's really what's going on. But I fear that I have it exactly backwards.
Oh, somebody got
it. It all starts with a simple problem. If you want to slide a mass from point A to point B, what shape of ramp will get it there the fastest?
I would be thinking something like a triangle. Like I'm pretty sure that they probably gonna switch that shape right there into a triangle.
This is known as the problem of fastest descent.
I might be wrong.
You know, common sense, you might say, take the shortest path. Straight line from A to B.
But if you bend the ramp down a bit at the beginning, well, the mass accelerates to a higher speed earlier. So even though it travels slightly farther...
So it's basically like, okay, you wouldn't slide down a real fast slide that has just a straight slope like that, right? But if the slide has that little bend in it where you could pick up speed from your weight of your body, then you would go faster down the slide compared to just a slide that's just straight, right? If it has a little dip in the middle, you'll end up going faster because it'll pick up the speed of your body weight going down faster than a straight slope would, right?
It travels faster and beats the straight ramp. So the question is, what shape provides the perfect balance of acceleration and path length to minimize travel time?
So I was definitely wrong about, it being a triangle that would get them there the fastest. It's looking like it's a L with a big time dip in it. Well, maybe two dips. At least I don't know what you would call that. But, I mean, How crazy is that? So if you've been, if all right, so if you, say if you were going in a car in outer space somewhere, and they said if you could drop your gravity or whatever it is, and you going down, and you pick up speed that way, and then you start going straight again, but you're still going fast, that would help you get to where you had to go faster, right? Which makes sense.
Time. According to Galileo, it was the arc of a circle. He showed that this is faster than any polygon. But is it the fastest? Nearly 60 years later, in June of 1696, Johann Bernoulli set this problem as a challenge to the best mathematicians in the world.
Mainly because he's a big show-off, and he wants to show that he's better than all of them.
A mathematician. Bro, that's a really interesting word. You know, I never really heard about that word too much. A math magician. Is that somebody who just comes up with math problems magically? Like how they do on them cards, how they try to trick you or pick this card. Did I pull your card? Did I pull this card? Like they didn't know in the beginning that that is the exact card that you pulled. Crazy, right? But it's true. They act like they ain't know that they just found it out of thin air, you know. And what? Maybe they have all the cards the same card. You never know. But I mean, that is just crazy.
He gave everyone 6 months to come up with solutions, but none were submitted.
How somebody gonna come up with solutions back in their day whenever they ain't even have no computers and stuff like that? Think about it. Ain't no AI helping them. Like what? How they gonna have 6 months? What they gonna do? Go look at a tree and think and think and think? I mean, what the heck?
Gottfried Leibniz, a friend of Bernoulli's, persuaded him to extend the deadline to give foreigners a chance.
And I think Newton was probably the intended target because everybody thought of him as the best.
Bro, whenever they used to mention Newton in school, I used to picture Cam Newton, that football player, because I never seen nobody named Newton, you know what I mean? Like, I used to really think that Cam Newton, the football player, was the one that came up with all this guy's ideas, but I was way wrong about that. Cam Newton, football player, just played for the Carolina Panthers and got drafted number 1 by the Carolina Panthers, and he played for the Auburn in college and everything like that. I ain't really like him too much as a player whenever he went to the NFL. I found he smiled into the camera and stuff like that too much when he playing against my team. But that's crazy. I'm happy to find out now that, you know, that it ain't no Cam Newton that I was thinking of all them times that I heard that and stuff like that, you know.
And so Johann would have wanted to show that he was better than Newton. He was no longer really active mathematician or physicist. He was working as the warden of the mint, like a big high government position.
Wait up. The warden of the mint? Is that what he just said? So even way back then, they had prisons where they had a warden that had bulls and cows and stuff like that in the farm? That's kind of confusing, huh?
And on the 29th of January, 1697, Newton returned home after a long day at work to find Bernoulli's challenge in the mail. Irritated, he wrote, "I do not love to be dunned and teased by foreigners about mathematical things."
Oh, he must have not appreciated that too much because he probably thought, you know, being in that time frame, you know, way back then, he probably thought that he was the smartest person in the world. So to see other people come up with ideas that's not the same that he had, it's like kind of like he don't love that idea, right? That somebody else might have had a better idea in the math world than him, right? Because at that time, you know, they probably thought, oh, they one of one in the way that they think, you know, and then they find out, oh, somebody had a more clearer understanding of the math than that person did, you know. So it probably did not make him happy knowing that somebody else might have been a little smarter in math than maybe he was at the time, and that probably, made him a little angry.
But the problem was too enticing, so Newton spent the rest of the day and night on it, and by 4 a.m. he had come up with a solution, something that took Bernoulli 2 weeks.
Boy, that is crazy. These people coming up with math ideas and then they get mad at each other. That's like a sport. It must have been like a sport back then. Whoever gets the math right wins the award. But bro, this is crazy. Like thinking back on how it must have been like back then must be crazy, because it sounds to me like, they did math all day long to try to get better than each other at certain math problems. I mean, that is just crazy. They probably wasn't even getting paid for that.
Newton submitted his solution to the journal Philosophical Transactions.
He sent his solution there but didn't sign it, and Johann Bernoulli, after seeing the solution, is alleged to have said, "I recognize the lion by his claw." Okay, you don't need to sign it, Newton. I can tell who you are. Who else could give such a...
So apparently the guy, after Newton had spent his whole entire day and night or whatever coming up with a better solution than what the guy had sent him, that guy was in shock. Like, not in shock, but he was like, I already know who sent me this new piece of math right here. It was from that guy Newton, right? And he was like, he understands the lion by his claw, meaning that he understands the math on the paper that is from Newton. That Newton had to do it because not that many people at that time were coming up with ideas like that and coming up with their own math like that and making it a more clearer understanding on things like Newton was probably.
solution.
And while overall Newton dominated Bernoulli, in this instance, Bernoulli's solution actually outshone Newton's.
I could see why Johann Bernoulli wanted to challenge everybody, because he came up with a really clever, I would say like a truly creative, beautiful solution.
To do it, he took inspiration from a problem faced by ancient philosophers. How does light travel from one place to another?
You want to know how light travels from one place to another? A sun around a planet. That's probably how it works, right? Because if you don't have no sun in your planet, how are you going to have light? From bugs with light, that's not going to cause too much light right there, partner. A bug with light, that's really not going to cause that much light. But if we didn't have the sun in the middle of our galaxy, whatever you want to call this universe right here that we in right now, if we ain't have the sun in the middle of our planets, we probably wouldn't even see no light or even be here. Our Earth would be way too cold to even be on Earth, because the sun provides heat and light, so we wouldn't have no light and we wouldn't have no heat, and the Earth probably would be super cold. So that's why, whenever they start talking about where does light travel to and stuff like that, it's kind of crazy. And another thing that I had learned about light that I found that was like super interesting is that if you're looking at another planet through a telescope, the way light travels is, if you see that planet through your telescope, you're actually seeing the light from that planet that was on that planet from like millions of years ago. Like, you're not seeing that planet like what it would be like right now at this second that we are living and watching this in. Like, you're seeing the planet's light in that planet from like 15 million years ago. So looking at something with a telescope, I learned from watching things about light, is that you're almost looking at a picture from 15 million years ago or something like that, because that's how light travels. So based on how far different things is, and like planets and stuff like that. Um, like you'll see it from a long time ago rather than seeing it, right? Like if somebody was to look at Earth from way over there, they would probably still see Earth like at a different planet. If they're looking at Earth, they would probably still see Earth as in the dinosaur age of Earth, that light from Earth.
This was contemplated by Hero of Alexandria in the 1st century AD. He realized that in a single medium like air, light always follows the shortest path. A consequence is that when light reflects, say, off a lake, the angle of incidence is always equal to the angle of reflection. Any other path between the start and end points would be longer.
And that makes a whole lot of sense, because think about it like this. If you take your phone light, all right, you take your phone light and you put it into a mirror, all right, and you put your phone light into a mirror, you could see, like okay, if you in a room with 4 walls, right, and you put your phone light on your mirror, you're gonna be able to see that phone light somewhere else on the wall. Like it's gonna be somewhere else on the wall. Like, so it's hitting the mirror and then it's hitting the wall after. Get what I'm saying? So it's like you're not pointing it at the wall, you're pointing it at the mirror, but because it's pointing at the mirror, it's hitting at the wall.
But when light goes from one medium into another, like from air into water, it bends in a peculiar way. It refracts, and it doesn't follow the shortest path.
And one of the reasons why light does that off of water probably is because water is kind of like a mirror itself. If you ever looking like if you ever look down at a puddle of water with at nighttime with some light behind your head, like a light ball or something, and you look down at the water, you could see your reflection, because water it kind of resembles a mirror in the fact that light bounces off of it and goes through it. Though light can go through water and bounce off of it.
If you've ever dropped something at the bottom of a swimming pool and you look for it through the water, if you put your hand in there, it's not necessarily where you think it is, because the light has bent away from the flat surface.
So what is the guiding principle here? Well, over the next 1600 years, people slowly figured out that the sine of the angle of incidence divided by the sine of the angle of refraction is equal to a constant, n, which depends on the nature of the two media. This came to be known as Snell's law, but no one knew why it worked. That is, until 1657.
So Snell's law. So I'm guessing that means, if you take light and you shine it onto water, that light will always, like say if you take a light and you shine it onto the ocean. Well, after you take the light off and it's no longer shining, where does that light that you shined on it, where did it travel to? It probably travels real slow somewhere, and that's probably why it's called Snell,
Another great mathematician enters our story at this point. This is Pierre Fermat. By day, he was a judge, but at night he'd come home and hang out with his wife and kids and then do what he really loved the most, which was work on math for fun. He mostly worked in pure math, but at one point he got interested in the question of why does light obey this principle of refraction?
And he thought maybe Hero...
And you know what's crazy is that if you would take your phone light and shine it onto a mirror, and then the mirror, if you had another mirror where the light off the first mirror would hit the other mirror, guess what? That would be like a double reaction to light, because the first mirror would bounce the light off of that mirror onto the other one, and then you could still see off of the other one light on your wall still. So it's like you shining your phone over here, lights going over here, and then going back over there. So that'd be like, you get what I'm trying to say, a double reaction to light.
Of Alexandria was on the right track, but it's not distance that is being minimized, but rather time. But to see if this was true for refraction would be difficult. He would have to work out every possible path light could take by varying the point where it intersects the boundary and compute the time for each.
Well, and another thing is, depending on how many reflectors things have, is that's how many different paths light can take, depending on how many different things are reflecting the light off of it. You get what I'm saying? It could be a mixture of things: water, metal, mirrors, um, a shiny car, like anything.
And then show that light takes the path for which the total travel time is the shortest.
He doesn't know how to solve it, and he worries that it's going to come out complicated even if he could solve it, so he's not going to do it. I think
It does seem like a tremendously tough obstacle to get around whenever you're talking about coming up with theories based upon light and things like that, because it's many theories you could come up with based upon light, probably.
it's because he wasn't super interested in physics, actually. But anyway, years go by. He gets interested.
It's like, why is your shadow always there? Always standing right next to you, being right by your side, helping you get through every single day. Why is your shadow always there, being cool with you? You get what I'm saying? It's like, what is that thing doing there? But that's all because of light, a shadow.
In it 5 years later and tries to solve it, and then he does solve it, and he shows that Snell's law actually pops out as the minimizing path for light, under these conditions of moving from one medium with one speed of light to another
that
with
is
another.
Crazy.
And that constant n, well, that's just equal to the speed of light in the first medium divided by the speed of light in the second medium, which allows...
So I see what they're doing right there. They're dividing the first light medium divided by the second light's medium. So that does make a bit more sense to me, in the fact that, if you're coming up with a theory, you need to get it down packed. So you need to understand exactly what the medium is for the light.
allows us to rewrite Snell's law like this.
This thing, I just want to read you a little quote because I love it. He says that this is the most extraordinary, the most unforeseen, and the happiest calculation of his life.
Oh, so whenever he said this was the most unforeseen and happiest, calculation of his life for a mathematician, it must have been a real breakthrough he came up with in the world of math, right? It had got to been, because when a mathematician says something like, something like that, what he had just said just now, that's probably what it means, right? It probably means that, it's like mind blown, like blowing that he could come up with a breakthrough about math the way that he had just did it, and the way he just found out.
See, it's good to do physics. If you use that principle of least time, you can explain everything that was known about light at the time of Fermat.
Man.
It's the first time, as far as I know, that anyone shows that nature obeys an optimization principle, that nature does the best possible thing. In this case, that light takes the shortest possible time.
Now, Bernoulli knew about...
It does make sense that nature works in the same way. Like even a human, whenever we want to do something right, we try to do it in the shortest amount of time possible. Whether it be taking a certain angle while we walk at something to get it in a faster time frame, or whenever you playing sports and you trying to get to somebody or something like that, and you take an angle to get there the fastest way, right? Or really even driving, taking a certain road to get somewhere a little quicker, like those type of things, is something that all humans go through,
Fermat's principle of least time, and he thought he could use it to solve the problem of fastest descent.
He converted the problem from a mechanics problem about a particle sliding down a chute to a problem about optics.
Instead of a mass that's accelerated by gravity, he imagined a ray of light that would go faster and faster as it went into layers of less and less dense media. And if you make the layers thinner and thinner, where Snell's law is obeyed at each interface, you eventually...
And then if it gets thinner and thinner for the light going down like that, it's gonna get faster and faster, probably. And another thing is, it's gonna probably steadily go on and go on and go on, right?
Eventually get a continuous curve. Now the question is, how should the speed of light change from one layer to the next so that it accurately models a falling object?
You could try to solve the problem by thinking if the particle has to fall from A to B, it's going to be picking up kinetic energy. It's going faster and faster as it slides down the chute, and it's converting the loss in potential energy into this kinetic energy. If you write down the conservation of energy for that relationship, you find that the velocity that the particle achieves at any time, having fallen a distance, let's say y, its velocity squared will be proportional to y, the height from the top.
And that makes a whole lot of sense, because as it's going down and going at a faster rate of speed to get to the point B, it's creating a much more distance for the Y. You get what I'm saying? Like the Y medium is becoming much more distance because of how fast its velocity is traveling to the point B. So it's like it's just like if we was to hop out of an airplane with a parachute on, like outer space becomes much more distant to us as we go down, because we're going down, you know. You get what I'm saying?
So velocity goes like the square root of y, and that'd be sort of like saying, imagine light moving in a way where instead of a constant speed of light, the speed of light is proportional to the distance from the top.
Yeah.
Now let's zoom in and look at a single interface. We can plug in our expression for the speed of light in each layer into Snell's law. Then you find that the sine of the first angle divided by the square root of y for the first layer is equal to the sine of the second angle divided by the square root of y for the second layer. And now here's the key insight.
But you see, the second label, it gets wider, right, as it's going down, right? Because as it's going down, it's creating a much more distance path than when it was starting to go down, right? So when it reaches that second layer, is the distance it's creating now is really widening. How do you say that? Widening its distance.
Snell's law also holds for the next layer, and there the ingoing angle is simply theta 2. So this is also equal to the sine of the third angle divided by the square root of y3. And the same goes for the next layer, and the next, and so on. In other words, this ratio must be equal to some constant, call it k. And this equation, the story goes, Bernoulli immediately recognized as the equation of a cycloid. That is the path traced out by a point attached to the rim of a rolling wheel. This is also known as a brachistochrone curve from the...
And a rolling wheel, as it's going, you know, if you put one point on the wheel, you're going to see, as you keep on pedaling the bike and going and stuff, you're going to see that it's just a repetitive motion of the tire, right? Going up and down, exactly what they show on the screen right there, how it's showing how the tire goes up and back down, moving in a circular motion, and that's just how motion physics work whenever it comes to dealing with something like that, like a bicycle.
Greek for shortest time.
And so the astonishing solution is that the fastest way to get from A to B is to follow an arc of a cycloid, not a circle, a shape called a cycloid.
Now, this curve
And you know what's crazy about this? That might be a reason why they came up with bicycles and bikes, because they found out that you could go faster on a tire that goes in a circular motion rather than what you would whenever you are walking. Now that's pretty interesting, because that would be an interesting to know. That'd be an interesting thing to know if you were wondering how they came up with tires for bikes and cars and stuff like that. That might be one of the reasons why they did that, because it could get you to point B faster than if you was trying to walk.
curve also has another surprising property. No matter where I release the mass from, it always reaches the end at the same time. For this reason, it's also known as the tautochrone curve, from the Greek for same time. Upon finding this solution, Bernoulli wrote, "In this way I have solved at one stroke two important."
And it makes sense that if you have two balls falling below the dip, and you take a ball and drop it while those two balls are dropping, and you take another one and drop it on top of the dip, that the one on top of the dip is gonna meet the two at the bottom at the same time that they reach the end, because the one at the top picks up a lot of speed compared to the ones that's starting at the bottom.
Important problems, an optical and a mechanical one, and have achieved more than I demanded from others. I have shown that the two problems taken from entirely separate fields of mathematics have the same character. Little did Bernoulli know, he was onto something much bigger. Around 40 years later, one of his students, Pierre-Louis de Maupertuis, also studied the behavior of light and particles, and he noticed that there are cases where the two behave very similarly. This made him think, what if Fermat's principle of least time wasn't the most fundamental? I mean, why should nature care about minimizing time?
And how would they not have plenty more theories to go along or verse this one theory? Why would there not be another theory of a triangle? You get what I'm saying? Instead of a circle, why would they not do one of a triangle or a diamond?
Maybe there is a more foundational quantity being minimized, one that doesn't only govern light, but also particles. So in the 1740s, he proposed a new quantity which he called the action. It is mass times velocity times distance. His thinking went something like this. The farther something travels, the greater the action. The faster it goes, the greater the action. And if it's a particle, then the more massive it is, the greater the action. If there are multiple segments to the journey, then the total action is just the sum.
And the bigger the mass is, the heavier. And you see, the heavier and bigger it is, whenever it is dropped, the faster it will pick up speed and go. But the lighter something is, like if you pick up a feather on side of the road or something like that, a feather, that's really light, you drop it and it's gonna float down. But if you picked up a glass plate and you dropped a glass plate at the same distance, it's gonna reach the ground way before the feather, because the glass plate has more mass to it, and it's gonna pick up more speed, being that it's made out of a heavier material that could pick up speed faster than a material made out of hair like a feather.
Of the mass times velocity times distance for each segment. To see the principle in action, here is a super simple example with no friction or losses. Imagine a 0.5 kilogram ball is rolled over the ground for 6 meters at 3 meters per second. Then that would be 9 units.
I think that's like 4 miles per hour, give or take. So 9 kg and MSV, all right, it's probably gonna be like 4 miles per hour.
Units of action. If the ball then bounces and travels another 6 meters at 3 meters per...
Now that don't make no sense though, because is there a wall hitting that table? Because why would the ball not roll off the table? why would it bounce off the end of the table like that? What kind of ball bounces off the end of the table instead of rolls off the table? So the way that this has to make sense is that there must be a wall right where that table ends right there, and the ball bounces off that wall and then keeps going up the table. Makes sense.
Per second, then the action for the whole trip is 9 plus 9 or 18 units of action.
So 8 miles per hour, right?
Now, what Maupertuis claimed is that out of all possible trajectories where the ball bounces off the wall, the path it will follow is the one that minimizes the action. In 1744, he wrote, "This action is the true expense of nature, which she manages to make."
So probably the action that he's talking about right now is probably, it's gonna follow the direction that it hits off the wall that it speeds up again for. It's gonna follow that same direction and that action that it took. Because whenever it goes that 4 miles per hour and then it hits against that wall, that's the action. Hitting against that wall is the action. And wherever it goes after it hits that wall is the direction it takes. You get what I'm saying? It makes sense.
What was the response to Maupertuis' revolutionary idea? He was attacked and ridiculed. One of his longtime friends, a fellow physicist named Samuel Koenig, wrote that not only is your principle wrong, you also stole it from Leibniz. Voltaire, who used to be a close friend of Maupertuis, accused...
Bro, that is really crazy. So maybe all these different mathematicians were mad that someone finally got it right. And now they started telling him that it's plagiarism, that that he just stole it from someone else and everything, and didn't add his own new meaning to it. That is crazy. That's what happens whenever people start to get mad at somebody for creating something that they could have created themselves, but they didn't at the time. So the person that created it first gets all the praise, right? So they get mad and try to say, oh, he stole it and everything like that, and it's not even true that he did that. He just came up with the right answer to the problem that everybody else was having trouble for.
Accused him of plagiarism, bad physics, being stupid, and just about anything else he could think of. In fact, he wrote a 32-page pamphlet just to mock Maupertuis. Of course, this may have been partly due to rumors Voltaire's lover had an affair with Maupertuis. But not everyone attacked him. Some just ignored him.
Maupertuis, I've taken a lot of math and physics in my life. I think you're the first person.
And you know what? They probably did that to him because he got the problem down pat. He got it right. He got the answer that everybody was searching for.
Person I ever heard pronounce it. He doesn't get much mention.
All of this was terribly stressful for Maupertuis, who was nearing the end of his life, and more than anything, he thought the principle of least action would be what he was remembered for. That would be his legacy. But now he was attacked, mocked, ridiculed, and ignored. Unfortunately, this treatment was at least somewhat justified, because Maupertuis came up with his principle by kind of just picking it out of thin air. There was no obvious reason why nature should care about mass times velocity times distance, or even...
But he probably put in the work to understand what it meant more than everybody else, and he probably got it right, and everybody else probably ridiculed him and told him that he just stole that, and told him that he didn't come up with his own answer. And because they were mad that they didn't come up with that answer first. He probably got it right the whole time. And they were probably trying to make him think that he didn't get it right so he wouldn't be remembered in history like everybody else wanted to be remembered in history. But if he got it right, he would be the first person to get it right.
Even less, why that quantity should be minimized. And mathematically, the principle of least action wasn't rigorous either.
Looks like you're getting a $3,200 refund.
Did she mention that at H&R Block, everyone gets their max refund or their money back?
And we always guarantee
100% accuracy on every return.
You had me at max refund. Switch to H&R Block and get 100% accuracy and your max refund guaranteed.
But there was one man who vehemently defended it, and that man was Leonard Euler.
Oh boy.
The first thing Euler did was he replaced the sum with an integral. So you could...
Did they say his last name was Euler? Does that mean that he has something to do with oil companies? Or in the oil field? And does his family have oil money? Maybe, you never know. Because if you have the last name of oil, wouldn't that be connected to oil around the world?
calculate the action while speed or direction changed continuously. And he used this to find the path of a particle around a central mass, like the orbit of a planet around a star. Solving this meant that out of every possible path between 2 points, he would have to find the one for which the action was the smallest. This is similar to the problem for
Oh, that, man, do you know what that's like, trying to find the smallest like answer to the problem like that? Oh my God, it's like trying to find a needle in a haystack. Like that SpongeBob SquarePants episode where he's looking for a needle in a haystack. You know how hard that would be?
Ma tried to solve, only now instead of changing one variable, he would have to vary every possible point along the path, which is infinitely many. Needless to say, this was an arduous task. Math had not yet developed the tools required to handle such problems.
Man, so that's
Fortunately,
really no joke.
Euler himself invented a new method. It was clunky and time-consuming, but it worked. Through this process, he realized that the principle of least action only works if the total energy is conserved, and it is the same for all paths considered. These were two conditions that Maupertuis hadn't...
Oh, hold on here. Oh my goodness. So the first theory came up with energy is conserved, okay? And energy is the same for all paths is the second one. But the thing is, the first one, energy is conserved. Listen here. It makes sense. Because for energy to just keep on going on, energy has got to be conserved somewhere for it to keep on going on and on, right? So it makes sense to have this type of equation right here where energy is conserved and energy is the same for all paths, because that's the only way that energy would be able to just keep on and on going.
hadn't realized were necessary. So Euler improved the mathematical rigor of the principle. He found two extra conditions, and he provided a specific example of it working.
Euler is an astonishingly powerful and not just great mathematician, but appears to be a good guy. As far as we could tell, he was very generous. You can still read Euler and really understand it.
So you see, he did have everything down packed that he needed, and that's probably why most of the mathematicians probably wanted to ridicule him and make him feel little, because they felt little because he got it right. You get what I'm saying?
He helps you. He's empathetic. You know, he was like you are, man. He's trying to explain stuff.
But Euler was still far from a general proof.
Oh.
That would have to wait for another legendary mathematician.
Oh my goodness, bro. So how many mathematicians do we have in the darn world? There should be only one. There should be only one a real mathematician, bro. Having all these different mathematicians like that, that's kind of really crazy to me. Like, think about it. Why would they need that many people coming up with math problems? Come on, man. Man, did they get paid for that? Like, coming up with different math problems? Boy, they probably spent all day long just to get paid from it. Boy, that is crazy.
Joseph Louis Lagrange. Joseph Louis Lagrange.
You give me about 5 or 6 years, I come up with better problems than them probably. Just from having AI on my side and everything like that, bro. So
was a shy 19-year-old, mostly self-taught. But despite his age, he was already working at the forefront of mathematics, including with Euler's new method. In 1754, he shared his results with Euler, who replied that Lagrange had...
Bro, 1754? Do they have a picture of this dude? Because you want to talk about 754, I don't even believe that. That is so long ago, it's crazy. That's like over 200 years ago. Maybe more than that. So think about that for a split second. And what kind of way would that even make sense to us, y'all? That don't make no sense to us. We not from those 17 something hundreds. Heck no. We from 2019 something. But I mean, they want to talk about something that's from the 1700s, though. I need some type of proof. They gotta have a picture of that dude or something, bro. Or a picture of what he wrote or something.
Had extolled the theory to the highest summit of perfection, which caused him the greatest joy. But besides being world-class mathematicians, the two had another thing in common. They were both huge proponents of the principle of least action. And around 5 years later, just a year after Maupertuis's death, Lagrange succeeded in providing a general proof.
Oh snap, so apparently this dude from the 1700s finally got the general proof right of the theory of everything, on the theory of everything. So let's find out exactly what he came up with in his general idea of proof of in the theory of everything. Let's see what happens here, because I'm having trouble focusing on the fact that somebody from the 1700s would be able to come up with a better idea than somebody from 2025. I'm having a real tough time thinking about that somebody from the 1700s could come up with a better mathematical idea than somebody in the year 2025 with all the technology and calculators that we have in today's world compared to what they had back then. We should be making breakthroughs every darn day in today's world. If they had that back then, they probably would have a breakthrough every single day in math.
Is there any intuitive way to think about action? I feel like there's an intuitive way to think about force, and there's kind of an intuitive way to think about energy. But
So an intuitive way, right? That's a big word, right? Intuitive, right? Think about it like this: is there a more focused way to think about a certain action? Think about it like that. Don't think about it as the intuitive word, right? Think about it as focus. Is there a focusing way to think about action? Is there a way that is simple? Is there a simple way to think about an action? Like, basically is what it means. Simple and focused. You know, if something is really focused, well, it should be simple. You get what I'm saying?
is there an intuitive way to think about action?
I don't know. I want to watch your show to learn. I hope you'll come up with it, because I don't have a good feeling about action.
Now, I want to explain Lagrange's proof, but I don't want to do it the way he did. So instead, we'll go through 3 steps. First, we'll explain the general approach Euler and Lagrange came up with. Then we'll rewrite the principle into its modern form. And finally, we'll apply this math to a simple example to show you why it works.
Well, the fourth thing here is I'm going to give my opinion about whether I think what they saying is right or is wrong. I'm going to give my opinion to see whether it's a modern form and why it works. I'm going to give my opinion to see if it's a general approach or not. So we're going to find out through my opinion, to be honest. So let's find out.
So first, the general approach. If there are infinite possible paths, how do you find the one with the least action? Well, Euler and
Well, if you want to find a path that takes the least amount of energy and action to get to a place, what you do is you look for the most straightforward path that is the shortest route to get there, right? And you break it down and you make it even more simpler. Basically.
And Lagrange realized you can do it in a similar way to how you find the minimum of a function. There, you take the derivative and set it equal to 0. And where the slope is horizontal, that must be the minimum. So if you took a tiny step to the left or the right, the value of the function basically doesn't change. And similarly, if you have the path of least action,
Oh, I understand that, because in the middle is where, there's no dips anymore. It has got to start from a dip in order for it to gain traction. That makes total sense.
then if you were to change it a little bit by, say, adding a tiny bump here or flattening it out there, imagine we're just adding a tiny function eta to our path of least action, well, then the action basically shouldn't change, because we're at this really special point, the path of least action. You add a little bit to the minimal path, but the action is still the same. If that is the optimal path that has the least action, then any other path must have more action.
I think that they just trying to, come up with something, but at the same time, it's still not making any sense. And what they say about stuff that don't make any sense, right? They say if it don't make any sense, it's probably not true. Okay? They say it's probably not true. Okay? So if what they're saying is not true, that would mean that they have another theory out there that is true. And we're going to get to that.
So the counter there is like all of this is the first order. So if you're looking at linear
what's going on right here?
terms that are proportional to eta, the deviation, then the first order.
Do we have a tall gray? Do we have a gray amongst us? Do we have a gray? Or a tall white? No? Okay.
The difference in action will be 0. The way you could imagine this is like, let's say you're at the bottom of a bowl and you're at the minimum and you make some tiny step away and we call that step eta. If that change would be proportional to eta, you would maybe increase on this side but decrease on this side, and then this would no longer be a minimum. So
right, because either one of those would become like it would have to be in the middle for it to become a medium, right? But because if it's on either side, it would definitely not be considered a medium anymore if it's already leaning towards one side.
sort of the coefficient of eta has to be 0. But since you're at a minimum, it kind of goes like a parabola. So it can be proportional to eta squared or potentially some higher.
But if it's in the medium of a circle, it's never going to be able to go up and down unless the medium of the circle changes like its physical shape, meaning that it flips over or something, and then it would go back to the medium it was. But first it would kind of just go around and then stop, at a certain point.
Order term. So there is a tiny deviation in the action, but it's not proportional to eta. So to first order, the change in action between the optimal path and some trial path is 0.
So what you can write is that the action of this trial path minus the action of the true path is equal to 0 to first order. This is a compact way.
Now that makes a whole lot of sense. That right there makes a whole lot of sense. You see that S? You see that S and that X and that T and that 0 and that equal sign? That all means something. But what does it mean exactly? You get what I'm saying? Because if that right there means something, that means that it has an actual meaning behind it. And we want to get in front of that meaning. We want to be able to understand that meaning. So here's the thing. If S is equal to 0 and Q is rectitude into T, so X and T could become 0 and S and O would become 0 too. So it makes sense about the velocity and the speed of these things.
way of writing the principle of least action, and it's the general approach you use to solve all these problems. So with that in hand, let's rewrite the principle into its modern form. Starting with Maupertuis's action, which is the sum of mass times velocity times distance.
Man, that is
But
crazy.
Euler changed this into an integral, so it's the integral of mass times velocity.
Look at that big old F. Mass times velocity times direction times speed equals 0. You gotta be kidding me. All them letters just equal 0. Why can't it be even simplified more than that? See what I'm saying about this kind of stuff? Looking at that right there, it look like I'm looking at Chinese, and I don't understand no Chinese. Why can't it be simple? Something like 2 plus 2 equals 4. Or 1 plus 1 equals 2. Or 0 plus 0 equals 0. How about you just show that? 0 plus 0 equals 0. You know what I mean?
Velocity integrated over distance. Now, the velocity is equal to ds over dt, which we can rearrange to get ds equals vdt, and plugging.
Why would velocity not be equal to mass over why would velocity not be equal to mass over what is it called? Let's see, heaviness. Like, why would velocity not be equal to mass over heaviness? You get what I'm saying? Or mass over heaviness times speed.
This in, we have an integral of mv squared over time. But wait, that's just twice the kinetic energy. And as Euler pointed out, the total energy must be conserved.
You see all that t plus 2d tt mv 2dt, all those type of things right here. It's like I'm looking at a bunch of mumbo jumbo. I want it to be really broken down. I want it to be like I'm looking at 1 plus 1, like I'm learning something. How you gonna learn that right there? How you gonna sit down and learn that right there? It look like a bunch of mumbo jumbo. Now here's the thing. It could be something. That could stand for something, but I don't think it does. You know what I mean? I think that's just a bunch of mumbo jumbo for anybody just to look at and learn something from. But how is most people supposed to learn something from this? This ain't no 1 plus 1 situation or 0 plus 0. It should be simplified. It should be simplified to 0 plus 0, something like that, to make us understand exactly how they come up with these type of letters equal 0 and stuff. Because to me, all those things that equal 0 is basically 0 plus 0 equals 0 to me.
Total energy is just kinetic plus potential. So we can rewrite this as T equals E minus V. And filling this in for the second T gives us...
So E equals T plus V slash 1, oh man, equals T and equals E minus V. So all that right there might equal 155. At the end of the day, that equate E equals T plus V minus 1 equals E minus V, probably 155. You get what I'm saying? If you want to do it by the numbers, it's probably going to be 155, y'all. And I don't even know what I'm talking about. But I just listen and I pay attention to these type of things, and I understand that ain't simplified. That's the exact opposite of being simplified. Simplified is whenever you go from x minus 0 equals 0. What you think x is going to stand for? 0. Because anything, if some is minus 0 and is 0, then it has to be 0. Because if it was 1 minus 0, it'd have to be 1. Because you're not really minusing anything from 1 if 0 is being minus from 1. It's like, say this right here, this cup. Say if I said, I want to minus this by 0. Alright, minus this by 0. I still have the cup. So it's like not being minused at all. It's basically like saying like 1 divided by 1 equals 1. because anything divided by 1 is probably, you get what I'm saying? Yep.
Us that the variation of t plus e minus v integrated over time is equal to 0. Now we can split this integral into 2, and since the energy is constant, we can integrate this term over time to get this. And we can simplify this even further. Just like with a normal derivative, we can write the variation of e times t as e times the variation of t plus t.
Oh, okay, here we go again. Here we go again with these weird letters. So now we got a ET equals EST plus TSE. Man, this stuff is just weird. I don't know why they wouldn't just simplify it for, you know how many views they would get if they would just simplify their stuff? Make it a situation that we can understand. You know, this is a critical review right here, partner. Like, look, just make it a situation that we can understand, because seeing all these different types of letters and all these things equaling 0, man, all that stuff to me don't make sense if it's 0 minus 0 equals 0 and stuff like that, you know, or 0 times 7 is 0, you know, like things like that. That's what makes sense. This is not broke down. This is like making the steps to realizing what this actually means even harder. So it really needs to be broke down into a much more simpler way. And believe you me, y'all watch this video enough, it's gonna get broken down into a much way more simpler way than something like this, if this video would get big enough for me talking about it. So that's just something to keep in mind out for y'all. Y'all make sure that y'all like this video and subscribe to the channel from watching this video and everything, because if this video gets big enough for me talking about it, it's gonna be huge what we gonna see next from these channels, right? If this video right here that y'all watching right now, my reaction, if it gets big enough, we gonna see a video come out that really simplifies this stuff, and it's gonna be like a 1 + 1 situation, but we ain't looking at all these things, but we gonna be able to understand it clearly. Because looking at all this, how would anybody, how would even Albert Einstein be able to understand these type of things clearly?
T times the variation of E. But remember, as Euler found, the energy of different paths has to be the same, so the variation between them is 0, and this term drops out. If we rearrange this like so, then we find that the variation of this integral is equal to minus the energy times the variation of time.
So minus the energy times the variation of time. It looks like minus the energy equals minus EAT. EAT to me. Eat. So, I mean, it ain't making no sense, man. This is just like putting a bunch of letters on a board and trying to get views. Y'all get what I'm saying? That's like trying to put a bunch of letters on a board in a video and posting that video to YouTube and then trying to get views from that video, acting like you real smart or something. Bro, that ain't even smart. Like that right there, that ain't even smart, because I know it could be simplified into making everybody around the world be able to understand it, rather than maybe 1% of the world understand it looking at it like this. You know what I mean? Like there should be some way of looking at this where 99% of people can understand it.
This looks a lot like some other minimization principle. If only this was equal to 0. Well,
And you know something else about this, what they're talking about in this video so far, about all these type of theories and mathematical problems and equations and everything like that. If this would be simplified down to a 1 + 1 equation where everybody can understand how to get these understandings of letters and everything like that, if it be broken down and simplified, you know the stuff that people would be able to come up with and be able to make, if this was just simplified and 99% of people would understand these type of equations. If 99% of people would understand these type of equations, technology would move at way more of a rapid level than what it's at right now. We would see floating cars and stuff like that probably.
We can make this zero by only considering paths that have the same travel time. If you do that, then there's no longer any variation in time, and this term drops out. And what we find is that Maupertuis's principle has changed into another form, where now the variation of kinetic energy minus potential energy integrated over time is equal to zero.
T minus V, kinetic energy minus potential energy, and then you integrate that along a path that you're traveling from A to B, and then integrate it with respect to time.
You notice how they use these big words, right? Integrated. What integrated means though is like it's trying to fool you into just listening to things that like you might not be that smart or something. But integrate means that like, you know, I know that y'all smart and everything, but integrate means that like you put it in. And then put it in with respect to time. Like so whenever he says and then integrate it with respect to time, it really means to put it in and with respect to time. You get what I'm saying? Like simplify what they saying, y'all. Whenever they talking, y'all gotta be able to understand what they saying. And if y'all don't understand what they saying, come look at my channel, because I'm gonna break it down and help y'all understand what they saying no matter what, you know, because I have trouble with this stuff. I have ADHD, so it's already hard for me to focus on what they talking about. But I could help a little bit, I guess, you know what I mean? Y'all watch my stuff, y'all probably learn more from me talking probably than what you would already learn from their video, because I already broke stuff down in this video that was easily to learn. But everything I seen in this video so far was kind of tough to learn.
It's all very strange, and yet that turns out to be the correct thing to integrate.
Now, this is a little weird. We started with mass times velocity integrated over distance, and now we have the kinetic energy minus the potential energy integrated over time.
Does that make sense to y'all? Look. Does that make sense to y'all? Let me know in the comments for real. I really want to know. If this somehow makes sense to y'all, let me know in the comments. Because this ain't making no sense to me. You know, it might be a confident video to listen to and everything, but this ain't learning nothing to me. This is like trying to take the hardest class of calculus they got. Or timetables, the hardest one. Like, what the heck, man? I wasn't no mathematician. But I could tell you even a mathematician looking at this understands that they only got one math number on this equation, and that's zero. And minus sign and equals. We don't see no other number on here to make it simplified. It should be simplified like 0 plus 0 equals 0. You get what I'm saying? If they had it like that, where we could all understand what they talking about, the world would be a whole different place. The world would be a whole different place if they had that. And if, you know, if y'all watch this video enough and somebody says, you know what, I'm going to make it simplified because people are liking that video, so I'm going to make one where it shows everybody the simplified version of this, where they all understand it, then we would all grow in understanding this stuff together and be able to actually make things based upon these equations right here. And that would improve everything in society and the world and everything if people just understood these equations simply.
Somehow, both are ways to write the principle of least action. But that also means that this integral here, t minus v integrated over time, is another way to write the action.
And t minus v integrated over time, you know what I mean? Like t minus v put in over time. That ain't making no sense to us, y'all. Come on, let's be real here. Like I bet you they have some. I want to see some science college educators talk on here in my comment section and let me know if they even believe in this mumbo jumbo. I want to know that for real. If they look at this and are like, oh yeah, that makes total sense. You know, because I feel like if somebody look at this and go, oh, that makes total sense. If somebody do that, I feel like they kind of lying. I really do. I feel like they kind of lying if they say, oh, that looks like total sense to me. I never thought that's how it would be. You know, this ain't like seeing, this ain't like learning what 1 plus 1 is. Boy, that's easy, right? Learning 1 plus 1. You like 2, and you're like 2, yep. And that becomes easy, right? But learning this here, man, it ain't gonna make no sense to nobody. Better yet, 9 million people on YouTube. I mean, come on. Does this make sense to 9 million people on YouTube? Forget that 9 million stuff. Does this make sense to 50 million people on YouTube? If we getting deep into this, does this even make sense to 100 million people on YouTube? And I already know. Y'all ain't even got to let me know that in the comments. I already know the answer. It's going to be no, it don't make sense to most people in those large crowd groups to make sense of this video, right? It'd probably be like 0.1% of them people that could understand this. You know what I mean? Like, cause I could understand stuff real easy whenever it comes to common sense. But this right here ain't even no common sense to me. This is like too many different senses to me.
The first person to write the principle of least action like this was William Rowan Hamilton in 1834. And by doing so, he got the principle named after him.
So the principle of least action that we write as integral of L dt, L being the Lagrangian, the T minus V, the kinetic minus potential energy, they don't call it Lagrange's principle, they call it Hamilton's principle. So I guess Hamilton is building on Lagrange in that way.
Yeah, well, I mean, I guess that's nice that they have a Hamilton principle. And, you know, I guess that can maybe be broken down to Hamilton's principle, you know. But at the same time, they have a Hamilton's hotel. I don't know if y'all ever been to it. It's real nice. I think it's out there in Houston, Texas, I believe. I mean, Houston, Texas. I think it's out there in Houston, Texas, or Dallas or something. A Hamilton hotel. So not only do they have a Hamilton math equation, but they also have a Hamilton hotel.
Hamilton's principle is the modern way of writing the principle of least action, and the way you'd find it in almost every physics book. In part, that's because Hamilton's principle tells you how objects move from one place to another, rather than just giving you the shape of the path. Two other important differences between both principles are that the action is now an integral over time instead of space, and a consequence is that with Hamilton's principle, you now need a start and end point, and also a start and end time. The third is...
You see, if you need a start and end point and start of end time, you know, those type of things should be simplified in order to make us understand what exactly he's talking about instead of just saying that in a short period of time and us, you know, it like even saying that in a short period of time, it's a lot to digest and take in and be able to understand like you would understand something simple. So that's just something to take into account when listening to a video like this and stuff like that, is that they give you so much information at one time that it's so hard to take in and digest and be able to understand exactly what they're talking about at the time, because it's so much. Instead of just giving you a piece by piece, even if they have to make the video longer, giving you a piece by piece explanation of everything would be better, because in that way you'd be able to understand everything as the time went on in the video. You get what I'm saying?
Is that with Maupertuis's principle, you need to keep the energy of different paths the same, but the time can vary, while with Hamilton's principle, the energies can differ, but the time has to be the same between paths. We have our general approach and the modern way of writing the principle, so let's apply.
Why not turn research into reality, into a faster way, into a faster meaning, rather than showing all these different type of things, general approach, modern form, and why it works and all this? Why don't they just turn a simple problem into a broken down problem. You get what I'm saying? Make it simple and then break it down even more to help the general public be able to understand all the things that this video is talking about. You know what the views would go from being on it would go from being 9 million to being like 100 million, 200 million views. You get what I'm saying? Because they have so many people on earth. They have probably over 1 billion people on earth right now. And that is a lot of people. So you could help a lot of people understand something that they would have never thought they could understand if it was broken down simply.
Apply it to a simple example to see why it works.
Let's say I throw this ball straight up in the air. So it goes from some start point to, say, a different end point.
So he throws the ball in the air. He throws it towards the sky. And then the ball goes through the air all the way up there and then comes back down and lands in his hand. And so you see that right there is a different, like that right there shows you a simple way of showing mass, velocity, and size of something, right? And what it's going to do and how heavy it is and everything, right? But that don't simply break it down, right? That really don't simply break it down, because whenever you throw the ball in the air, you're just going to catch it again. You know, and your hand might move while you're trying to catch it and stuff like that. So it's not like you're really seeing, you know, if you would just let the ball go in the air and then bounce off the ground real high and then be able to see it fluctuate like that, how it stops bouncing and everything like that. That's a different way of looking at it.
In a certain amount of time. Now, if we call the height of the ball y of t, then we can plot these 2 points like so. And then we can imagine infinitely many possible trajectories that could connect these 2 points. Some go a little higher, some lower, some have wiggles, others don't. The only condition is that all paths must have the same start and end point and the same amount of time elapsed between them.
Now, to find the real trajectory,
Now, if we're all being honest right now, and we look at this chart, can any of us, I want y'all to even let me know this in the comment section, because I'm actually interested in knowing this. Does anybody on here know what that chart means? Looking at it. If you're just looking at that chart, would you be able to understand what that chart means by looking at it? Let me know. Let me know in the comments, because I would love to know what y'all thoughts are about looking at this chart. Do y'all think that it should be something broken down and really simplified rather than being this drawn out with it? You get what I'm saying? Rather than being so hard to understand that it's almost like thinking to yourself that you'll never be able to understand this just by looking at it or hearing it, right? Let me know.
proceed as before. We imagine that this is the true path, y of t, the one with the least action, and then we imagine making small variations to it by pushing it up a little here, down a little there, and so on, making tiny changes.
So it looks to me like all he did there was make the lines more squiggly. Because whenever he was talking about the ball just went straight up in the air and back down to his hand. So what are we seeing a graph for with squiggly lines in it when the ball just went straight up and straight back down into his hand? What are we seeing squiggly lines for right now, y'all? Let's make sense of this. Let's break this down together.
At every time step, which we'll call eta of t. So when you add y and eta together, you get this new trial path. Let's call it q of t.
And what's up with this eta of t? Where does this eta come from? ADA. Where does this ADA come from? Eta. All right. Is this a name of a hurricane or something like that? What exactly is this for? You know, like all of a sudden giving a t a name, eta. You get what I'm saying? What is eta for? Why can't it just be like 1 + 1 = 2? 2 + 2 = 4. 5 + 10 = 15. You know, 3 + 30 = 33. Why can't it be something like that? Simple to understand. Why does it have to be eta times t with Paul is woman? Why does it have to be something that we don't even understand at all or even have any knowledge about? You get what I'm saying? This is why it's a critical review. This is why I'm trying to say if somebody would just simplify this stuff for all of us to understand, we could then make stuff that the world never thought would be imaginable, because everybody would have a simple understanding of how physics and relativity work, and the theory of everything works.
And since the variations are small, the difference in action between these two paths is 0.
Oh my goodness.
Our next task is to solve this equation. So we compute the...
Now I really want to know if anybody out there would understand this stuff. So all he did was make them two lines colorful. Does that stand for numbers just making it colorful? I mean, come on. Like does a blue mean 3? Does a red mean 8? Does a blue mean 250? And does a red mean 1,400,000,000? You know, it's hard to understand, right? But it's easy to get.
The action for each path. For this, we need the kinetic and potential energy for each, and we write them as a function of y and eta. Plugging that in, you get the difference in actions is equal to this. But wait.
Boy, that's super smart. Look at that, y'all. But I really want y'all to try to bring in a science educator on this one. Someone in college, you know, that teaches college. I want to see if they even understand this right here. And let me know in the comment section, because to me, if it can't be simplified more than that, no, how is anybody supposed to understand this? If it can't be simplified more than that. You know, I understand 1 + 1, 2 + 2, 30 + 10. Easy. Real easy. But this kind of stuff right here don't make no kind of sense. You know, I want to make a challenge. You know, let's get this video big enough to where someone breaks this down and makes it simplified to a 1 + 1 equation equals 2. Okay, help us all be able to understand this in a simplified way. In a way that we could all understand it. Not just a few people here and there. And heck, seeing this video, looking at this equation, maybe no one out there would be able to understand this equation. Maybe it would be really hard to understand. Maybe it is just a bunch of mumbo jumbo. But we want to know. We want to be able to understand this fully. Because in our lifetime, if a lot of people are able to understand this fully, this equation fully, looking at it right now, people are not going to be able to understand it fully. But in our lifetime, if they do understand it, we are going to see some revolutionary things come about.
This first integral is just the action of the true path. So these integrals cancel, and what you're left with is just that. M times dy over dt times d eta over dt minus eta times the derivative of the potential integrated over time is equal to 0. We can rewrite this further by using integration by parts. That allows us to replace this term with this one.
Oh. So we won't replace a term that's in that box above the box with the last equation that's already in the box. That's the one that we want to replace the one at the top with. And after that, we're going to make an X. We're going to cross that one out. And then we're going to put the one that's right there. We're going to put that one to the left. And we're going to make it a whole new equation. It makes a lot of sense. But at the same time, it makes no sense.
And if we plug that in, we now have some function that when multiplied by eta...
Hold on here, we're going to put some taller lines in it. We're going to put some circle things that don't match. We're going to put some numbers on that L. Hold up here.
And integrated over time has to be equal to 0. But since eta can be just about anything, this can only be true if this part is 0.
Oh,
so
it can
what
only
we
be
found
true.
is that the action is minimal for
Did y'all hear that? It could only be true. And if only we knew if it was true or not. Because looking at it, I can't tell you a final answer. I can't say true, not true, I don't know, maybe. Looking at it, it's like a big 0% to me. That's what it looks like, 0% understanding.
for the path that satisfies this curious differential equation. Now, it might look complicated, but it's not. Minus the derivative of the potential is just the force.
Did y'all hear that just now? Did someone just say it might seem like it's a little complicated, but it's really not? Am I the only one that just heard that? Ain't no way I'm the only one that just heard that. Bruh, what might seem complicated doesn't just seem complicated. It's all the way complicated. This is a critical review, partner, and this thing is all the way complicated.
And the second derivative of height, well, that's just acceleration. So if we rearrange this, we find that the path that satisfies the principle of least action is the one that obeys F equals ma.
I don't know about all that. I don't know if F equals ma, for mom, I don't know if, and I highly doubt it. You know that from all those things, I didn't even see a F in the first, all those different math problems that he had up there just now. I didn't even see a F in one of them. So where he gets an F from? Frank, family, Frankenstein. Where does he get an F from on this list right here? Funny movie, Frank Sinatra. Where does he get a F from those different equations? Can anyone explain this in the comment section even? If y'all explain it in the comment section, I'm gonna make a whole video about it. And I'm gonna break this down and simplify it like y'all ain't never seen it simplified before. It's gonna be like a 1 + 1 = 2. And y'all be able to understand it real quickly.
In other words, the principle of least action is equivalent to Newton's second law. But it covers more than just mechanics. Fermat's principle of least time turned out to be nothing more than a special case of the principle of least action. So with this single principle, you could suddenly describe...
Y'all, if we was to look at this video and try to make sense of it, it would not make any sense. And that's all I was trying to say throughout this video. Is that if anybody out there could look at this video and simplify it to a 1 + 1 or a 70 + 70, even a 70 + 70 equals what equation? Probably be 140, right? If they could even turn it into an equation that's simplified like that, it would be revolutionary to the entire world. Thank y'all for watching.